we're talking about first, and then look at how things fit into that definition. Which is locked. Oh, I'm sorry. It's locked. Maybe we should grab it. All right. We're just talking about candy. Didn't say. What's your favorite kind of candy? Okay. Those are good. So we got a few Snickers here. All right. So let's define acids and bases, what we mean by that. It's actually not that trivial to define that because there's actually different ways of defining it. So if you've taken chemistry in the past or you've been in some other classes where there's talk about acids and bases, there's different ways that you can define what makes an acid or a base. We're going to stick to the definitions that are most useful when we talk about things like biological systems. If you get into some other chemical reactions, they can have some different things, but we're going to stick with these. These particular definitions are named after the people who proposed them. So this is called, oops, if I spell it right, this is called a Bronsted-Lowry definition. So we'll write the definition and then we'll talk about what it means and look at some examples and how we can apply that. So our first definition is an acid is a molecule. Let me make sure I use the same, or substance that donates hydrogen ions. So an acid is a molecule that donates hydrogen ions. And we'll look at some things. We'll talk about how we can tell whether something is donating hydrogen ions or not in a minute. So then a base is going to be kind of the opposite of that. A base is a molecule that accepts hydrogen ions. And we should note, if you look at this in your book, rather than the word molecule, they use the word substance because there are substances that are not molecules that can act as acids and bases. But the examples that we'll be seeing here will be molecules, so it's okay to say it that way. Yeah, so that's a different definition of acids and bases, is that acids donate H and bases donate OH. That's another different kind of a definition. We will see that most of the bases we look at have OH in them because the hydroxides, those tend to be basic. But this definition is a little bit more general. It involves some other molecules that may not be OH. All right, so that's our basic definitions. That may not make a whole lot of sense yet. So let's look at an example and look at how this really works in a chemical reaction. So I'm going to write a chemical reaction here. It's a little different from ones we've seen before. Doesn't really fit into that category, into one of those categories from the last chapter, or a couple chapters ago. But let's think about what's going on in this reaction based on those two definitions. So one way we can describe what's happening in this molecule, in this reaction, is that it describes a transfer of an H+. H hydrogen ion is moving from one molecule to another. So how would you describe that? Which molecule is it moving to and which molecule is it ending up on? Or which molecule is losing H and which molecule is gaining H? Yeah, the H2O is gaining the H and becoming H3O+. And that means the HCl is losing the H and becoming Cl-. So you see how that works in there? So how would you apply those definitions then? Which molecule is acting as an acid? HCl, yeah, because that one's losing its H+. So this one's acting as an acid. And that means that this one is acting as a base. It's accepting that. So one thing to notice here is that those definitions are defining an action or a role. It's saying that an acid is a molecule that does something, that donates H+, which means that molecules don't get to be defined as just acids or bases forever in every situation. It depends on what they're actually doing in the chemical reaction. Let's look at another one.
Real quick,
Yeah.
for the H3O, after the O because you gained them.
Right, because it was neutral.
Accepted.
It was neutral. It gained a positively charged hydrogen ion. So now the whole thing is positively charged. Yep. This molecule is ammonia, NH3. And we're going to look at what happens when it reacts with water. So when ammonia reacts with water, we get ammonium and hydroxide. So, same question. This reaction works the same way as the one before. There's a hydrogen donator and a hydrogen ion acceptor. Which one is which? Which is the acid in this situation, in the second reaction? NH3 is losing is donating its hydrogen? Well, okay, so on the left are the two things that we're deciding from, the two participants in the reaction. And the right we can think of as like the results of that. So as this thing moves from left to right, what happens is a hydrogen transfers from the H2O to the NH3, which makes it NH4+. So now it's got an extra one. So we would say that the NH3 has accepted the hydrogen, and the H2O has donated it because of then where they end up. So that means that we call this the base, and this the acid. Based on those definitions. So right away we see, based on these two examples, that acid and base is not a fixed definition. It depends on the situation. In the first example, water is acting as a base. In the second example, water is acting as an acid. So you have to look at the reaction to be able to tell if something is an acid or a base. All right. The other part of this is the other thing that we're going to do a little bit differently from what we've done before. Acids and bases in these reactions can actually go back and forth. So rather than just going from left to right in the reaction, we can also go from right to left. So we can draw an additional arrow here to show that these reactions are actually going back and forth. And we can define acids and bases on the other side as well. So we can say if you started on the right and you went to the left in that first reaction, which one's the acid? H3O. It's got to be because it's the only one that has any H. So that's the one that's donating the H. And then we would say that the Cl is accepting it. So on this side, this one is the acid, and this one is the base. The nice thing about doing this is there's always one of each. So if you have trouble defining one or the other, as long as you get one of them, you know the other one is the other. So if you were pretty sure that that one was the acid, but you weren't sure that the Cl was the base, well, it has to be because it's the only other thing there. So if you can get one of them, the other one has to be the opposite. What about in the second reaction? Which one is acting as an acid in that one? Yeah, NH4. It's donating its hydrogen over to OH minus, we would say, if we're starting on the right and going to the left. So the NH4 is the acid, and the OH is the base. So in acid-base reactions, and we would define these as acid-base reactions, each side is always going to have an acid and a base. And they're going to kind of complement each other. And we have a special word for that, and the word is conjugate. So whenever you have an acid on one side of an acid-base equation, there's going to be another molecule on the other side made up of mostly that same thing, except for the H+. And we call those two things conjugates. So this acid and this base are conjugate because they only differ by H+. So let's define that. The rest of the molecule is the same, but they've either lost or gained H+. And so then those two things become, we call them conjugates. So every reaction, every acid-base reaction will have two pairs of conjugates. The other pair is the other two. H2O and H3O plus are conjugates of each other. Conjugate acid, conjugate base. We do the same thing, define it on in the second reaction here. Right, the NH3 and the NH4 plus are conjugates because they're the same except for H plus. One has an extra H plus compared to the other. And the same thing with those, the H2O and the OH. So next to our definition of conjugates in an equation, let's put a couple more so that we can actually find the conjugate acid and base absent an equation. So a conjugate acid is whatever the molecule is that we want to find with an extra H plus. So in our example above, in our first example, if we wanted to know the conjugate acid of water, when water reacts with an acid, it forms H3O plus, which is called hydronium ion. We'll get into that a little bit later. So we would say hydronium is the conjugate acid of water because they are conjugates of each other. Similarly, we could say that water is the conjugate base of hydronium ion. So we can define a conjugate base as whatever the molecule is minus H plus. Let's make a chart. We'll put some molecules in here. And let's see if we can list the conjugate acid and conjugate base without looking specifically at a reaction. So if I put water here, to find the conjugate acid, what you do is look back at the definition. You add H plus. So you're adding a hydrogen and you're adding a positive charge. So the conjugate acid of H plus is H2O is H3O plus. We've added H, we've added a positive charge. For the conjugate base, we take away H and we take away a positive charge. So if we had H2O, which is neutral, and we take away an H, we get OH. But we also take away a positive charge, so it has to be OH minus. If you take away a positive charge from neutral, you get a negative charge. And that's the thing that I think people mess up most about doing this, is the charge. It's easy to add or subtract the H, but then you forget you also have to correct the charge. So you either have to add positive charge or take away positive charge. Yep.
Would there ever be like a number?
Sure. Yeah, there could be. So let's look at that. So let's say instead we start with OH minus. We start with a charged molecule. So what's the conjugate acid and conjugate base of OH minus? Well, conjugate acid is what we get if we add an H plus. So what do we get if we add an H plus to OH minus? Well, we got to add an H plus. So you add the plus, which gets rid of the charge. And then you add the H, which is H2O, yeah. So we'd get rid of the charge because we went from negative to 0 because we added a positive charge. And then we also now have an extra hydrogen there because we added H plus overall. We added the H, we added the plus. All right, so now what happens if we take the conjugate base? In the conjugate base of OH minus, we need to take away H and take away plus. So what do we get if we take away H and take away a plus? We get O, just O, and what would the charge be? If we take away another H plus. It starts, so we started at -1 with OH. If you take away a positive from -1, what do you get? 2 minus, right. So we're going negative now. Minus, 2 minus as we take away that charge. It might be helpful, just like sometimes we think about in math class, if you think about like a number line, and so when you take away H, let's just write it. So here's 0, 1, 2, 3, -1, -2, -3. So if you were neutral and you took away H plus, to subtract H plus means you're moving to the left because you're taking away positive. If you're adding positive, you're going this way. If you're adding positive, you're taking away positive. You can think about moving the charge that way. Let's look at some other ones. What if we look at ammonia, NH3? Can we write in the conjugate acid and the conjugate base of NH3? Right, so the conjugate acid, we're adding positive and we're adding an H, so we end up with NH4 plus. And then what do we get if we take away H plus, if we make the conjugate base? Yep. Right. NH2, and that one ends up minus. So if you start with a neutral molecule, the conjugate acid will always be +1 and the conjugate base will always be -1. If you start with a -1 molecule, it'll be 0 and -2. So those will always be the same because we're always just losing H plus. Okay, what about an acid like this one? H2CO3, this is called carbonic acid. This one actually doesn't have a conjugate acid. You can't add more hydrogen to it, but what about a conjugate base? What would be the formula? HCO. Yeah, right. Thanks. So we lose one of the hydrogens and get HCO3. And then since we started neutral, if we lose a positive charge, we have to end up with a negative charge. And so we can then also look at that molecule itself. We can say, what's the conjugate acid of that? Well, that's just going to be the one we started with, H2CO3. We start with a negative, the conjugate acid is going to be neutral. And what would the conjugate base be for HCO3 minus? Yeah, carbonate ion, so CO3 2 minus. So we take away hydrogen, we take away a +1. All right. So why is that useful? Well, one reason is that we know what happens to these molecules now in an acid-base reaction. So if I said, what do you get if HCO3 minus reacts with a strong base? Well, that means that it's going to lose its hydrogen and become the conjugate base. So it gives us a way of predicting what's going to happen. This becomes really important in things like in biological systems or in other types of solutions when we want to know what kind of ions are present. If we're using an acid, we might also expect to see the conjugate base present. If we are using a base, we might see the conjugate acid present. So we might be able to think about what types of things are in solution if we can do this, if we can think about how this would behave in an acid-base situation. All right, so that's basically how these reactions look, and this idea of conjugate acids and bases. Let's take a little bit of a change here and get into some naming. I know we just got done saying that acids and bases are not labels that we give to molecules all the time, but there are some molecules that really only act as acids or bases. And so in the names of those compounds, we usually put the word acid because that's what they usually do. So how do you identify them first? Formulas for acids usually start with hydrogen. There are some exceptions to that, like water, which is H2O, but is not always an acid. But other molecules that act as acids, generally the formulas start with H. So that's your clue that you need to name these things like acids and not using other techniques that we've done naming for. There's two categories of acid. One's with oxygen and one's without oxygen. We'll do the without oxygen first because those are a little bit simpler. There's just not as many of them. So if it doesn't have oxygen in it, we're talking about things like HCl, HBr, HI, HCN, things like that. Now, how do we name those? If it doesn't have oxygen, we put hydro and then the thing with an IC at the end, ic. So we would call HCl hydrochloric acid, right? So anybody want to take a guess on HBr? Close, but it's an acid, so we're going to name it like an acid. So we're going to name it the same way, hydrobromic acid. And that's really the way that you remember these, or the way that you should do this. You don't have to memorize a whole list of names. Think about one that you know. Remember hydrochloric acid, since that's the one we use all the time. And then just think, okay, this other thing kind of looks like hydrochloric acid, so I'm going to name it the same way, but just with like a different word in the middle. So what do you think HI would be? Yeah. Yeah, so you see how that works? It's iodine instead of chlorine or bromine. So we put iodo in the middle there instead of chlor. And also, like, I realize there's a couple choices there. So this could be hydroiodic acid or something. Like, if you do something like that on a quiz or exam, that's fine. I don't have a problem with that as long as you're using the right idea to get to the name. Sometimes different parts of it are cut off in different ways, and that's okay as long as you have a general idea of how it should go. HCN is a little bit trickier because you have to know what CN is, because that's not, again, it's not carbon, it's not nitrogen. Anybody know what CN is? Yeah, CN is cyanide. So if that ion is cyanide, how would you name HCN? Yeah, exactly, right. Hydrocyanic acid. And that's most of them that are in that category. There's HF, hydrofluoric acid. That's about it. There's a lot more of them on this other category, which are the ones that do have oxygen in them. So when they do have oxygen, it works a little bit differently. Let's say in a molecule like this, HNO3. When they have nitrogen or an oxygen, you leave off the hydro on the beginning, even though they still start with the H in the formula. You leave off the hydro, and you name them based on the name of the ion. So NO3, what is the name of that ion? The ion is what? What's NO3 as an ion? -1. Nitrate, yeah. So you take that name nitrate, and you put the ic on the end, and you make this nitric acid. So it comes from nitrate. Let's do this way. Let's go the other way here. So if we had sulfuric acid, how would we figure out the formula for that? Right, so we first have to think about what ion it would come from. And the fact that it doesn't say hydro at the beginning tells us that it's one of these oxygen-containing ones. And the ion from sulfur that has oxygen in it is sulfate, right? So we know that this thing is going to be based on sulfate. So sulfate is SO4 with a charge of -2. So then what does the formula have to be in order to have a neutral compound overall there for sulfuric acid? Right, H2SO4. So that's how we know it's H2 and not just H. It's not that you have to memorize a bunch of different formulas. You know sulfate is -2 because we remembered that we memorized that back in chapter 6 or something or whatever. And now we can just add 2 hydrogens to it to neutralize it because every hydrogen has a +1. So then we have a neutral compound, H2SO4. All right, try this one. Phosphoric acid. So use the same technique. Think about what ion is it based on, and then how many hydrogens do you have to put in there to balance it out and make it neutral. Yeah, thanks. So again, if we go back, we would base this on the phosphate ion, which we know is PO4 with a -3 charge. So that tells us we need 3 hydrogens attached to it to make it neutral. H3PO4. There's several like this. There are some different names. there's some different ions that would change the ending to OUS, so like sulfurous acid. We're not really going to get into all of those. Let's do one more. We'll go back the other way. I'll give you the formula, and you tell me the name. So if it's H2CO3, what would you call that? Right, but what about just CO3? What's that ion? That's carbonate. So how would you name the acid? Yeah, carbonic acid. And again, if you throw an extra syllable in there or something, carbonic acid, or you cut something off and just call it carbic acid, it's fine. It's fine. As long as you're using the right procedure. The most important thing is you recognize these as acids. So if there's just like on the next exam, there's a bunch of stuff that says name these things. It doesn't tell you what category they're in. So you have to recognize that they're acids and should be named as such. And how are you going to recognize that? What do you look for? Well, that's part of it, but it's the H that comes first, right? So you look for that H first. All of these examples start with H. And then you would name the rest of it depending on which category it falls in. But what about the one that's based on hydroxide? So OH minus is hydroxide. So how would you name that? Maybe. We have another. These are all good ideas, but not quite there yet. There's a better name that we would use for this particular one. Nothing? All right, we'll just put it here. So this is water. It's got 2 hydrogens and an oxygen. So. You know, so don't overthink it. You know what it is, right? So just remember, water is one of those exceptions that it looks, if you put it in the list with everything else, it looks like an acid. We know it can act like an acid, but we don't name it like an acid. We call it water. All right. So that's how we name acids and acids. We don't name bases anything special. We haven't really talked much about bases yet. So let's look at them. Bases aren't any particularly special, different kind of molecules the way that acids are. So they're at times harder to identify because we don't know what kind of molecules can accept hydrogen. Remember, that was the definition. You really need an equation to tell you that. But there are some molecules that usually act as bases. So one large class of basic molecules is the hydroxides, metal hydroxides. So that's things like sodium hydroxide, calcium hydroxide, whatever, some metal with hydroxide. Those generally act as bases. And in those particular compounds, it's just the hydroxide that's doing the work. So when we think about how these would act in an acid-base reaction, so let's look at that. We'll take an acid like HCl, and we'll react it with sodium hydroxide, NaOH. The products of that reaction are water. And NaCl. But one important thing to notice about this is that the sodium isn't really doing anything in this reaction. So remember our last chapter. What happens when sodium hydroxide dissolves in water? What's physically happening when you put a salt in water, like sodium hydroxide? You put that compound in water, what happens to the ions? Do what? Yeah, the water molecules surround them and they separate, right? So the fact that we write NaOH, especially if it's an aqueous solution, which it is here, that doesn't mean a thing that's stuck together. That means you've got sodium ions and you've got hydroxide ions in solution. And remember that NaCl is kind of the same thing. That's aqueous too. And even though we write NaCl in an equation, if we really think about what's happening in solution, you've got sodium ions, you've got chloride ions. They're not together, they're separate. So when we think about what's really happening in this reaction, notice the sodium here doesn't really change, doesn't really do anything. It was separate floating around in solution at the beginning. It's separate floating around in solution at the end. But the hydroxide has changed because the hydroxide has accepted that hydrogen and become water. So this is going to get messy, but if we take this, right, that's the thing that accepts this hydrogen and then becomes water. That's kind of the key to the reaction. The hydroxide takes the hydrogen and becomes water. So when we write these bases, they're usually these metal salts, but what's really happening is just the hydroxide part is doing the actual reacting. And the metal is just floating around. Right. There are other bases that are not sodium hydroxide or not hydroxides. We looked at one up here, ammonia. So anything that can accept a hydrogen from water is considered a base. And since ammonia does that, that's considered a base too. When you clean with ammonia, I don't know if anybody's ever cleaned with ammonia, but when you buy a solution of ammonia for cleaning, it's not actually NH3. NH3 is a gas. When you put it in solution with water, it actually makes ammonium hydroxide, NH4OH. But because that reaction is reversible, it's going back and forth, and it sometimes makes some ammonia, and that's the smell that you get if you ever smell that ammonia cleaning solution. So it started as ammonium hydroxide in the bottle, but as it goes backwards and forms ammonia gas, then you can smell it. So that's an example of a base as well. So we can identify our acids, we can identify our bases, and then we can also remember that there's a lot of molecules that can go either way. They can act as an acid or a base depending on what is happening in that particular reaction. All right. Good so far? Yeah? All right. The other important part of the chapter is about acid-base strength. So that was kind of the identifying stuff. And then we're going to get into strength. But to get into acid-base strength, we have to do one other thing first. Because we have to talk about something called equilibrium. And the book kind of does this in the opposite way, but I think it makes more sense to do it this way. Okay, so let's imagine a chemical reaction. And I'm going to pull up a figure from the book here so we can see what we're talking about. maybe. If it wants to load. Oh, so this is page 322, or 332, sorry. I'm going to look at this little graph over here. All right, so what's happening in this graph is you've got time on the x-axis and concentration on the y-axis. So this is a graph that's showing what's happening to the concentration of the molecules, what's happening to the amount of the molecules as the reaction goes on. So it starts at the beginning, which is on the left, and then proceeds to the end, which is to the right. Let's look at each curve individually. So we'll look at the red curve first. When you start a reaction, you have a really high concentration of reactants, and you have a really low concentration of products. You have 0 products because it's the beginning of the reaction, right? So you have a bunch of reactants, you have no products. And then as the reaction goes on, the amount of reactants decreases. Does that make sense to you? Think about it in your head. You're doing the reaction, the reactants are used up, so they're not there anymore. At the same time, if we look at the blue curve, that's the products, you start with 0 product, and as the reaction goes on, the amount of products increase. Makes sense, right? As you do the reaction, you're making more and more products. Okay. Once you get to a particular point in the reaction, you will no longer lose reactants, and you will no longer make any more products. Everything will just be balanced out, and nothing will change anymore. And that point is called equilibrium. So the point at which there is no longer any change in products or reactants. And specifically, we're talking about amount or concentration. So you start, you got all the reactants, then they start to get used up, and at some point, they're not getting used up anymore. And the reason for that is because of this idea of this double arrow that we saw in one of the reactions above. So let's look at a typical acid-base reaction. We're just going to use generic letters, so we're going to say HA is the acid, and B is the base. And the hydrogen is going to transfer from A to B. So we're going to end up with A minus and HB plus, because the H plus transferred. And then since this is an equilibrium reaction, that means that it can go backwards and forwards. So what happens in this reaction is the reactants start going, making products, but then when they get to a certain point, the products are also going backwards and making more reactants. So the reaction is proceeding in both directions. And we may get more products or we may get more reactants, but we're never going to be 100% in one side or the other. We're just going to be at a particular state. So that's the other thing. If you look at the graph here, equilibrium does not mean that you have the exact same amount of products and reactants. It just means that they're not changing anymore. So you could have way more products, but that's as many as you're going to get, or you could have very, very few products, and that's as many as you're going to get. When it stops changing, that's what we call equilibrium. So all acid-base reactions are like this. All chemical reactions are like this. They have some degree of equilibrium where they can go a little bit backwards or a lot backwards, depending on the reaction. And the other neat thing about equilibrium is you can kind of control it. And the best way to think about this is with water. And I don't know why this works so well, but it seems to be the easiest way to think about this and have it kind of make sense. So let's say you've got 2 tanks of water that are connected by a pipe. What's going to happen? Those tanks are going to even out, right? The water's going to go through the pipe and back and forth until everything's however it wants to be. Let's say you dump some more water in one side. What happens? Yeah, it shifts until it like rebalances. So when you put a stress, that's called a stress, you put a stress on one side, the whole system has to rebalance to accommodate that, get back to equilibrium, get back to the nice, even situation. And the same thing happens in a chemical reaction. So if we look at that reaction on the top, this thing is at equilibrium, and then we add more HA, we add more reactant. Well, the whole system has to compensate for that. So it's going to now, assuming there's enough B around, it's going to push the whole reaction to the right, just like the water, and rebalance. And the net effect of that rebalancing is to form more products. So if you have a reaction at equilibrium, you put more in one side, we're going to balance that out on the other side to form more of the other side, just like the water. All right. So how does that work, or how do we think about that? Let's use an example or a question from the book. This thing is called Le Chatelier's principle. That, again, is not really important, but the principle is important. The name is not so important. So here's a reaction that's at equilibrium. It's going back and forth, and it's balanced out at some point. It's an acid-base reaction. So what happens is the reaction going to shift more toward the reactants or more toward the products when each of these things happen. So first, if we add some CHO2 minus, which direction is that reaction going to get pushed? We'll just say left or right. Is there another left and right? Okay. So if we add some more CHO2, which way does the reaction have to get pushed to compensate? More to the right or more to the left? Sorry, I'm opposite you. Left. To the left, yeah, because we're putting in the stress on the right. So just like saying adding some more CHO2 is like saying we're going to dump more water in the right side, and that means it's going to push the whole thing over more to the left. So we're forming more of the stuff on the left. We didn't talk about this specifically, but what if we remove some HCHO2, which is the thing on the left? So if we remove something from the left, what has to happen to the reaction to get it to rebalance? Is it going to move more to the left or move more to the right? To the left, yeah, right, just like the water thing, right? You take some water out of one side, it's going to push more water over to that side to recompensate for it or to balance it back out again. So both of these are examples of stresses that would move the reaction more to the left. All right. What about C? What about if we remove some H3O plus? That's the right, right? So you're taking out from the right, so the whole reaction has to go more toward the right to compensate for it. From kind of a practical standpoint, let's say you're doing this reaction because you want to make CHO2, that thing on the right, CHO2 minus. That's like your product. So you want to make that, so you do the reaction, and it balances out at a particular equilibrium spot. And that's as much as you can make. Well, then what you could do, if you could remove the H3O plus somehow, use a chemical or something, you could remove it, well, then you could make more of that product that you wanted. And so those kind of ideas or this kind of idea can be used to manipulate the reaction to get it more to the side that you want it to be at, as well as just something that we understand. we're going to look at this more when we talk about things like adjusting blood pH and that kind of a thing. So finally, the last one, if we add some HCHO2, which direction does the reaction get pushed to? The left or the right?
Right.
To the right? Why?
Because since you're adding some to the left, it's going to push some over to the right so you balance.
Yeah, right. You see that? So does it help to think about the water thing? It's like you're dumping into the left, which is then going to push more over to the right. Yep. Okay. So this idea, as I think we'll see, is really important with regard to acids and bases because most acids and bases also follow this kind of idea and have this back and forth kind of action going on in their reactions. So when we get to that, when we do the next part, which is going to be defining the strength, we're going to define it in terms of the equilibrium. So the first thing to note, the biggest misconception about acids and bases, is strength has nothing to do with how dangerous or bad for you or corrosive an acid is. Strength refers only to the electrolytic capacity of it, meaning does it form ions in solution or not? And it has to do with the equilibrium. So what that means is strong acids or not form, sorry. Strong acids dissociate, which means they break apart completely in solution. That's it. Doesn't mean they're bad for you, dangerous, whatever. It just, if they're strong acids, they break apart completely in solution. So HCl is an example of that. And that reacts like this. We've already seen this. HCl, if you put it in water, forms hydronium ion and chloride ion. So it breaks apart completely. The H goes with the water, the Cl stays Cl. And what happens here is the equilibrium of this reaction lies very, very far to the right. So far, in fact, that it really almost makes more sense to not even have that backwards arrow. So this reaction, we would say, is truly a one-direction reaction. When you put HCl is a gas. When you put it in water and make hydrochloric acid, make that solution, the H and the Cl are no longer bonded together. They have broken apart completely and formed ions. So if you remember back to when we did the solutions with the light bulb, the HCl solution made the light bulb go really bright because there's lots of ions in that solution that can conduct the electricity. So strong acids conduct electricity. They are strong electrolytes. And the interesting thing about strong acids is there's only 6 of them. Now there's some other things that kind of go in that category, but the strong acids we can actually name are HCl, HBr, HI, HClO4, which is perchloric acid, sulfuric acid, and nitric acid. So those are the 6 acids that are considered strong acids that completely dissociate in solution. You don't have to remember all those formulas, but as you might notice, it's a few of the ones that we use most commonly. HCl, H2SO4, HNO3, we've used all those in lab. And that's because that property of being a strong acid, breaking up completely in solution, makes it really useful in reactions. It's sort of like a pure source of that hydronium ion. So they end up being used a lot. So every other acid besides those is technically a weak acid. So weak acids dissociate, we might say, somewhat. So an example of that would be HF, hydrofluoric acid. The reaction kind of looks the same. I'm going to leave the arrows out for a second. We'll put them in a minute. So HF can break up. The H plus can go with the water. The F can end up by itself. But what happens here is, because it's a weak acid, that reaction does not go to the right. The equilibrium actually lies more on the left. And one way we can express that is by putting a really small forward arrow and a much longer backwards arrow. So we would say this reaction mostly goes to the left. At equilibrium, there's very few products and mostly reactants. And that makes HF a weak acid, because it's not forming a lot of products. It's not dissociating much in solution. Most of HF is actually whole HF molecules, not broken up ions. Now that said, HF is one of the most dangerous acids that there is. So this is where it doesn't make sense to associate strong and weak with like danger. HF is one of those, well, first of all, HF eats glass, so you can't keep it in glass. You can only keep it in plastic or metal. It will eat rocks and bones, stuff like that. So if you wanted to like get rid of a body, you could probably do that.
You used to drink that.
Yes, although I think it doesn't actually work because there's other stuff going on. But if you had some pure stones, you could eat through a wall with it. You could eat through bricks, things like that. So like HF is a really nasty acid. We don't even keep any in this building. Like we just, if there was something we need to do with HF, we would probably just say, no, we don't want to, like, is it really that important to do it? So it's bad stuff, but it's still under the category of weak acids because of its equilibrium, because of how it forms ions or doesn't form ions in solution. All right, let's take a break there, and we'll come back. We'll talk about how we describe this equilibrium and how that leads to this pH scale, and what that means and how we calculate that. And then we'll talk about buffers, and that'll be it. All right, so see you about 15 minutes. I have to restart the computer too, so I will